Here is a standard block on a ramp type problem that we'll be examining from a work and energy point of view. We'll be computing the work done on the box by each of these four forces. Then we will compute the net work done on the box, two different ways, and then we'll apply the work energy theorem. Here's our scenario. A box of mass m is pushed a distance d up a ramp. So we will be going distance d up the ramp that way, inclined at angle theta. It's pushed by a constant force, Fa. That's this force right here on my free body diagram, applied parallel to the ramp. We're given the coefficient of kinetic friction between the box and the ramp, mu k, the initial velocity of the box, v1. That is pointing up the ramp, we're told. Number one, find an expression for the work done by each of the following forces in terms of the given variables and little g. Then compute a numerical value for each work, assuming these numerical values for the mass, the distance, the angle, the magnitude of the applied force, the coefficient of kinetic friction, and the initial speed. Let's note that on our free body diagram here, each of these four forces is going to be constant. They're all constant as the block slides up the ramp. So noting that all forces are constant along the path as the box travels up the ramp. That's going to simplify our work calculation. The definition of work is given by this integral, but if the force is constant along the path, then the integral simplifies to just this expression here. We just need the sum of the products of the components of the force and the components of the displacement. So that's all we need since our forces are constant in this case. Work done by gravity, Wg will then be Fgx delta x plus Fgy delta y, and we can see that there's no movement in the z direction here. Okay, so clearly I have to pick some axes here. I've got my free body diagram. Now if we align our axes with the acceleration, block is going to accelerate up or down the ramp. So let's tilt our axes. Let's have the x direction point up the ramp in the direction of the applied force, y direction perpendicular to the ramp. And then note that our displacement in the x direction, that's the distance d, and our displacement in the y direction, that would be perpendicular to the ramp, would be 0. Okay, noting that, let's check these terms to see if any of them are 0. Delta y, that's 0. Okay, so that term drops out. We'll be left with this term right here. Before we go any further, I'd like to predict in each case whether the work done by that particular force will be positive, negative, or 0. And we can tell that, recall, just by comparing the direction of the force with the direction of the displacement. So gravity pointing straight down, force of gravity points straight down, our displacement points in that direction. We can see that the angle between them is greater than 90 degrees. It's an obtuse angle, so the force of gravity is somewhat opposing that displacement. Therefore, gravity will be doing negative work on the box. We can tell that. Okay, so this work should come out negative. All right, we'll need to break gravity up into its components, given that choice of axes here. So let's make it the hypotenuse of a right triangle. We can see that this angle here will be congruent to our angle theta right there. Those are both theta. And then Fgx, our x component, will be minus mg sine theta. Minus because it'll be pointing in the negative x direction. Okay, so Fgx is minus mg sine theta, and our delta x is positive d. And there we go. This expression is indeed negative as we predicted. Plug in the numerical values, do the arithmetic, and we'd get a value of about negative 99.4 Newton meters. Newton meters, the unit for work. Okay, next, the work done by the normal force, Wn. That'll be Fnx delta x plus Fny delta y. Let's predict the outcome. Normal force points in that direction, but our displacement is at a right angle to it. So we already know the answer. That force being 90 degrees, being perpendicular to the displacement, will not be doing positive work or negative work. It'll be doing zero work, neither speeding up the block nor slowing it down. So this should come out to be zero. Let's examine in detail how that comes to pass. Fnx is zero. There's no x component to the normal force, and delta y, once again, is zero. Therefore, no work done by the normal force. Work done by friction. Ffx delta x plus Ffy delta y. Okay, let's predict. Force of friction points down the ramp. Our displacement points up the ramp. They're 180 degrees apart. That'll definitely be negative work done by the force of friction. It is opposing the displacement. So this should be negative work done by friction here. Let's see in detail how that works out. Delta y, as before, is zero. The x component of friction. Okay, so it's pointing in the negative x direction here. We know our expression for the force of friction. Kinetic friction, since we're sliding, will be mu k times the normal force. So negative mu k times the normal force. And then our delta x is the distance d. Okay, so that is our force of friction right there. And our normal force, we can tell from our balance of forces in the y direction. Our normal force must be equal in magnitude to the y component of gravity, must be equal to mg cosine theta. So this becomes negative mg cosine theta times mu k. Oh, forgot to slip that in there. Times the delta x, which is d. There we go. Minus mu k mg cos theta times d. If you were writing this up formally, you would want to indicate off to the side. You'd want to state the equation that ffk equals mu k fn, and then you'd also want to state that the sum of forces in the y direction is fn minus fgy equals zero. Communicating to the reader exactly how you arrived at this expression here. So you'd want to state those two things off to the side. Now we can plug in our numerical values for all of these. Let's see, as long as we're talking about the proper way of showing your work, we should be showing that we're plugging in numerical values. I skipped that step here, but let's do it here. Minus mu k is 0.2, m is 8 kilograms. You always want to show the numerical values you're plugging in. Little g, we understand what little g is. It's not necessary to plug in a value for that. Cosine theta, cosine of our 25-degree angle, and then times our distance d, 3.0 meters. There, that's better. This time we've shown the numerical values we're plugging in for each of those variables before we get our numerical answer. Do the algebra or the arithmetic here, and we would get about negative 42.6 Newton meters. The work done by the applied force, lastly. So there were 4 different forces on the free body diagram, therefore 4 different works, potentially, up to 4 works to calculate, 1 for each force. Work done by the applied force will be Fax delta x plus Fay delta y. Our delta y is still 0. Delta y is still 0. Fax, that's just our applied force. It's pointing in the plus x direction. Magnitude is 40 newtons. So we could just write here 40 newtons times our displacement. Sorry, I should put an intermediate step here. Let's write Fax times d, and then show our numerical Fax times d, then show our numerical substitutions. Variables first, then numerically. 40 newtons times our distance d, which was 3.0 meters. We get a positive 120 Newton meters. Positive makes sense because our force and our displacement are in the same direction. They're supporting one another. They're parallel to each other. Therefore, positive work being done by that applied force. Okay, so we've got numerical values for each of the works done by each of the forces that were being applied. Now, let's find the net work done by all the forces on the box in two different ways. First thing we can do, and the thing that makes the most sense given the effort we've already gone through here, would be to calculate the net works by just summing up the numerical values of the works done by each of those forces. So the net work is the work done by G plus the work done by the work done by the force of gravity plus the work done by the normal force plus the work done by the force of friction plus the work done by the applied force. So we have the numerical values for those. Negative 99.4 plus 0 minus the 42.6 plus the 120. Those are all in Newton meters. Include those units. Sum those and it comes out to about negative 22.0 Newton meters. Okay, that's the net work done on the box. And before we go any farther, let's consider what it's telling us. It is negative. What's that mean, that the net work done was negative? How did that come to be? It looks like the positive work done by the applied force was not as big as the combination of the negative works done by gravity and friction. So even though the applied force was adding energy as the box moved up the ramp, friction and the x component of gravity were removing energy at a greater rate, or they removed more energy than the applied force added. So in sum, the box lost energy here. So what does that mean happened to the speed of the box as it went up the ramp? I'll leave that to you to think about while we go on to find an expression for the net work according to this expression. This is the second way I want to calculate the net work. We're going to make use of the idea that the net work done on the box is equal to the work done by the net force on the box. So if we find the net force and then compute the work done by that net force, that will also give us the net work, and we should be able to get this same value. Okay, so we're just trying this calculation from this perspective instead. Looks like we'll need to compute the net force in the x direction and the net force in the y direction. We want to do that in terms of the given variables n, g, and then use that expression to compute a numerical value. Then we'll verify that our result agrees with number 2 here. So net force in the x direction. We have our applied force minus our force of friction minus the x component of the force of gravity. So that is the applied force minus mu k mg cos theta, we determined that earlier, minus mg sine theta. Those are our expressions for those two components. And then the net force in the y direction, we already worked out that that's Fn minus mg cos theta, which is 0. No net force in the y direction. So the net work given by this formula, which is basically this formula right here, except net work equals net force x component, net force y component, net force z component. And again, this is only valid because the forces were constant along the path. Net work equals the net force in the x direction times our delta x plus the net force in the y direction times our delta y. Our delta y is 0, and for that matter, the net force in the y direction is also 0. So that term is very much vanished. So we're just going to multiply the net force in the x direction times the displacement in the x direction. Our net force in the x direction is this expression. So Fa minus mu k mg cos theta minus mg sine theta, all that times the displacement d. Okay, I might simplify that a little bit. I've got an mg here and an mg there. I might be inclined to factor out that mg and write it as Fa minus mg times the quantity mu k cos theta plus sine theta. This is just a matter of preference. I think it looks nicer written that way. And at this point, we would plug in our numerical values. So let's do that. This is 40 newtons minus our 8 kilograms times little g, our mu k, which is 0.2, cosine 25 degrees plus sine 25 degrees, times our distance, 3 meters, which comes out to approximately negative 22.0 Newton meters, which is indeed in agreement with our earlier calculation. Negative 22 Newton meters. Okay, so we did that in two different ways. I wanted to show you how these two expressions are equivalent to one another. So the net work is both the sum of the individual works, and it is the work done by the net force. Lastly, let's now apply the famous work-energy theorem. Our work-energy theorem here. The value of finding the net work done on an object is that we can then apply the work-energy theorem to determine the change in kinetic energy of the object, to determine whether the speed increased or decreased. We can compute the speed of the box after it has traveled distance d. So we can compute now the final speed of the box. So our change in kinetic energy is k final minus k initial. So 1/2 m v final squared, that's our final speed squared, minus 1/2 m times our initial speed squared. And I want to rearrange this to solve for our final speed. So let's see, I can add the 1/2 m v1 squared to both sides, and then multiply both sides by 2 over m. So let's do that one step at a time. This becomes delta k plus 1/2 m v1 squared equals 1/2 m v2 squared. Then multiply both sides by 2 over m and square root both sides. So v2 magnitude, the final speed, will be equal to 2 times delta k over the mass plus v1 squared square rooted. And here's where the work-energy theorem comes into play. Delta k is equal to the net work done. So if we plug in our numerical values, we would have 2 times delta k, which is the net work done, which is this negative 22.0 Newton meters. So this is approximately then negative 22.0 Newton meters divided by our mass, which was 8 kilograms, plus our initial speed, which was 4 meters per second, squared. 4.0 meters per second. That gets squared, and we're square rooting that whole expression. Okay, let me double check, make sure no typos here. Looks good. Okay, run the arithmetic, and that should come out to be approximately 3.24 meters per second. Let's think about that answer. Does it make sense? A little more than 3 meters per second. Compare that to the initial speed, which was 4 meters per second. This is indicating that the box slowed down. It was slower at the top than at the bottom. Does that make sense? Is that consistent with what we found? The box slowed down, which would indicate that it lost kinetic energy, which would indicate that the net work done on it was negative, as indeed it was. Negative 22 Newton meters. The net work was negative. Therefore, overall, the forces had a net effect of removing kinetic energy from the box. The delta K was negative 22. Delta K was less than 0. It lost kinetic energy. Therefore, it slowed down, ended up at a lower speed at the top than it started with at the bottom.